Alicia Andy Perez, Francis Conrad M. Esteban, and Sanjo Ernest P. We're going to share our knowledge about place value through millions, solving involving division and other operations, and what is a prime number and a composite number.
Today we are going to teach you about place value through million in math. Every digit in a number is a place value. But Sanjo, what is a place value?
A place value can be defined as the value represented by a digit in the number on the basis of its position in the number.
Thank you, Sanjo. Now we are going to show you an example showing the relationship between the place or a position and the place value of a digit in a number. In 13,548, 1 is a 10,000 place and its place value is 10,000. 3 is in the 1,000 place and its value is 3,000. 5 is a 100 place and its value is 500. 4 is a 10 place and its value is 40. 8 is a 1 place and its value is 8.
Francis, we can show them that a place value chart can help us in finding and comparing the place value of the digits in a number through millions. The place value of a digit increases by 10 times as we move left on the place value chart and decreases by 10 times as we move right.
That is right, Sanjo. So it means in 3,287,002 is 263. 3 is in million place and its value is 3 million. 2 is a 100,000 place and its value is 200,000. 8 is a 10,000 place and its value is 80,000. 7 is a 1,000 place and its value is 7,000. 2 is a 100 place and its value is 100. 6 is in 10 place and its value is 60. 3 is a 1 place and its value is 3. That is all, guys. I hope that we help you to understand the place value through million.
I will teach you of what prime numbers are, their examples, and the difference with composite numbers. First, a prime number is a natural number greater than 1 that cannot be formed by multiplying two smaller natural numbers. A natural number greater than 1 that is not prime is called a composite number. For example, 5 is prime because the only ways of writing it as a product 1 times 1 or 5 times 1 involve 5 itself. However, 6 is a composite number because it is a product of two numbers, 2 times 3. They are both similar than 6. Primes are essential in number theory because of the fundamental theorem of arithmetic. Every natural number greater than 1 is either a prime itself or can be factorized as a product of primes that is unique up to their order. There are infinitely many primes as demonstrated by Euclid around 300 BC. No known simple formula separates prime numbers from composite numbers. However, the distribution of primes with the natural numbers in the large can be satisfactorily modeled. The first result in that direction is the prime number theorem proven the end of 19th century, which says that the probability of a randomly chosen number being prime is inversely proportional to the number of digits, that is, to its logarithm. Several historical questions regarding prime numbers are still unsolved. These include Goldbach's conjecture that every even integer greater than 2 can be expressed expressed as the sum of two primes and the twin prime. Conjecture that there are infinitely many pairs of primes having just one even number between them. Such questions spurred the development of various branches of number theory, focusing on analytic or algebraic aspects of numbers. Primes are used in several routines in information technology, such as public key cryptography, which relies on the difficulty of factoring large numbers into their prime factors. In abstract algebra, objects that behave in a generalized way like prime numbers include prime elements and prime ideals. A natural number 1, 2, 3, 4, 5, 6, etc. is called a prime number or a prime if it is greater than 1 and cannot be written as the product of two smaller numbers. Natural numbers greater than 1 that are not prime are called composite numbers. In other words, n is prime if n items cannot be divided up into smaller equal-sized groups or more than one item, or if it is not possible to arrange n dots into a rectangular grid that is more than one dot wide and more than one dot high. For example, among the numbers 1 through 6, the numbers 2, 3, and 5 are the prime numbers, as there are no other numbers that divide them eventually without a remainder. 1 is not prime as it is specifically excluded in the definition. 4 equals 2 times 2 and 6 equals 2 times 3 are both composite. The divisors of a natural number n are the natural numbers that divide in n evenly. Every natural number has both 1 in itself as a divisor. If it has any other divisor, it cannot be prime. This ideals leads to a different but equivalent definition of the primes. They are the numbers with exactly two positive divisors, 1 and the number itself. Yet another way to express the same thing is that a number n is prime if it is greater than 1 and if not of the numbers 2, 3, and 1 divides n evenly. The first 25 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. No even number in n greater than 2 is prime because any such number can be expressed as the product 2 times n2. Therefore, every prime number other than 2 is an odd number and is called an odd number. Similarly, when written in the usual decimal system, all prime numbers larger than 5 end in 1, 3, 7, or 9. The numbers that end with other digits are all composite decimal numbers that end in 0, 2, 4, 6, or 8. Are even and decimal numbers that end in 0 or 5 are divisible by 5. The set of all primes is something denoted by p. Here I will show you a table of all prime numbers up to 1,000.
First, we need to know the parts of division calculus. Dividend, the number that you have to divide. Divisor, the number that the dividend is being divided by. Quotient, the result of the division. Remainder, what left over after the division. Now, let's see how a one-digit divisor problem would look we replace each other with a number. We want to divide 243 pieces of candy among 5 friends. The dividend will be 243 because it's the number
We have to divide 24 by 5. So we need to look for a number that gives us when multiplied by 5. Since an exact number doesn't exist, we have to use the closest number, smaller number. 4 times 5 equals 20. In this case, 20 is the closest number to 24 that those surpass it. So we write 4 in the quotient and subtract 20 from 24. And we have 24 minus 20 equals 4. There's only one more step for us to do in order complete in one digit division problem. Bring down the next number from the dividend and repeat step 2. We bring down the next number, which is the number 3, and write it next to the number 4. The complete number is 43. Now we need to divide 43 by 5. We have to find a number that gives us 43 when multiplied by 5. But since it doesn't exist, we have to find the closest number to that doesn't surpass 43. In this case, it's 5 times 8 equals 40. So let's write the 5 in the quotient. And the 40 underneath. The 43 to subtract 8. 43 times minus 40 equals 3. There are no more numbers in the dividend. So we are done with the division problem. The answer to our one-digit division problem is every kid will get 48 pieces of candy and 3 pieces of candy will be left over. Addition is bringing 2 or more numbers together or things together to make a new total. Other names for addition are sum, plus, increase, and total, and the number of to be added together are called the addends. 9 plus 3 equals 12. 9 and 3 are added. 12 is the sum or total. Subtraction is taking one number away from another. Start with 5 apples, then subtract 2. We are left with 3 apples. Multiplication is repeat addition where we see that 6 plus 6 plus 6 make 18. 6 times 3 equals 18. 6 is the multiplier. 3 is multiplicand. 18 is the product. These are simple problems involving division and another operation. I hope you learned something from Keisha. That's all, folks. We hope you learned from our discussion today. Thank you and